Hello, welcome to Fouraye Education. Today I'll be teaching financial mathematics and stochastic calculus. So this will be a new series involving financial mathematics and, as I said, stochastic calculus. So how I'll structure the series is that in the beginning I'll be introducing some basic concepts and then moving on to more complex concepts, transitioning into stochastic calculus, and then looking at how we apply the concepts of Ito calculus and stochastic calculus onto finance and option pricing. And so in this first episode, I'd like to introduce some very elementary and basic concepts at which we will build upon in order to understand more complex and more structured and more detailed concepts, basically. So to start with, I want to introduce a very, very rudimentary and very, very important concept for financial mathematics, the sigma algebra. Now, sigma algebras are sort of one of the heart components of financial mathematics. You have to know this in order to perform stochastic calculus. So, sigma algebras. What are sigma algebras? Sigma algebras are a sort of topology similar to semi-algebras or that sort of thing. But to define sigma algebras, let's say we have a set given to us, omega. The sigma algebra associated with this set, let's call it F, is a collection of subsets that apply to three conditions. So the sigma algebra is in fact a collection of subsets. Now this is very important to understand in order to visualize it later on, that the sigma algebra is in fact just a big collection of different subsets. Now the first condition is that the set omega has to be an element of the sigma algebra F. The second condition is that any subset A of omega has to be an element of the sigma algebra F, and any complement of A has to be a member of the sigma algebra. Now, what this second condition implies is that if there's a set in the sigma algebra, its complement has to be within the sigma algebra, which, if we look back under the first condition, implies that if omega is in the sigma algebra, then omega's complement, the empty set, is also a member of the sigma algebra. And on to our third condition. Our third condition states that for a given collection of subsets of the sigma algebra, the union sum from 1 to infinity of the given subsets have to be a member of the sigma algebra. Now, these are some basic laid out rules in order for us to understand what sigma algebras are. Now, I want to give attention to a very important sigma algebra, a special sigma algebra known as the Borel sigma algebra. The Borel sigma algebra is a sigma algebra generated by open sets. So what I mean by this is if we assume X a subset of Rn, or perhaps X a subset of a topology, or X topology space, or X metric space, whatever you want. Basically, we want open sets. Through these open sets, we'll generate a sigma algebra known as the Borel sigma algebra. Now, this sigma algebra contains all of the empty sets within that space, and naturally, its complements. Now, this was a noteworthy sigma algebra, so I had to mention it. Getting back onto sigma algebras, how do we visualize sigma algebras? How exactly do sigma algebras look like? And how do we imagine and work around them? So I have a very useful diagram in order to visualize how sigma algebras look. Imagine a timeline of events. If we have omega over here, we'll have subsets of omega A and B. B being the complement of A and A being the complement of B. This is how we can visualize the sigma algebra. Now in this scenario, the sigma algebra at hand would be the sigma algebra containing omega, the empty set A, and a complement, or in this case B. So if we have a something that contains omega A and B, this would not be considered a sigma algebra because it doesn't contain the empty set. And if you look at another thing where it contains omega empty set A and B, oh sorry, no B. So if it only contains omega empty set and A, this would not be a sigma algebra because it doesn't have a complement. It needs the complements of the subsets as well in order to be a sigma algebra. Now that we understand what sigma algebras are, we need to look at the concept of measurability and measures. Now, what are measures? Specifically, what are probability measures? Before we understand what probability measures are, we have to comprehend the concept of measures. Measures are a function, per se. So, measure. Now, if we assume a probability space, omega, and a sigma algebra F, a function which maps the sigma algebra to the real space is a measure if the first condition being for all of the subsets in the sigma algebra, the measure the measure of the subset will be bigger or equal to 0. The second condition being that the measure of 0, or the measure of the empty set, is 0. And the third condition is that the measure of the union sum from 1 to infinity of the subsets is equal to the summation of 1 to infinity, 1 to infinity of the measure of the subsets. So these are the conditions which require a function to be a measure. A function which maps a subset from the sigma algebra to the real realm, at which the values given for each of the subsets are bigger or equal to 0. The empty set nets 0, and the measure of the union sum from 1 to infinity of the subsets is equal to the sum from 1 to infinity of the measure of the subsets. So those are the conditions to be a measure. Now, what is a probability measure? A probability measure is a measure such that omega gives 1. Now, omega is our probability space. So the probability of all events happening is 1. The probability of the probability space is 1. Now that we have the measure, the sigma algebra, and the space, or omega, we can form this notation, which we see a lot. This notation denotes our working grounds, this being our probability space, this being our sigma algebra, and this being our measure. Now this is the basic concept of measures and sigma algebras. In the next part, I'll be continuing on with random variables and measurability and a little bit of expectations. Thank you very much for listening, and I hope you'll like and subscribe.